Hi everyone, and today we're gonna talk about ionization energy. So what is ionization energy is what we want to know before we begin with everything. So it's the minimum energy required. Okay, let's say this is an element A. So the minimum energy that is required to remove an electron from an isolated gaseous atom. Now I have written here G to denote that it's a gaseous atom. Okay, is known as ionization energy. So the minimum energy that will be required in that case. Now let's understand this here. So here let's assume this is a boron atom where it has 5 electrons and 5 protons in it. So this is going to be the nucleus. Now if we have to remove one electron, we'll be requiring some energy, and that minimum energy required is your ionization energy 1, because for getting this one electron out, the first electron, it's your ionization energy 1. Okay, now here your atom looks like this. Now the energy that was required in this process was an ionization energy 1. Now to get this electron out, this is going to be your second electron. Now as you can see, now your electron has become B positive because it has lost one electron from B to B positive. Now in order to remove this electron, you will require some more energy. That minimum required energy that will be required to get the second electron out of the atom will be your ionization energy 2. And here now you have this B2 positive. Now you have to remember one thing, that your ionization energy 1 is lesser than ionization energy 2. Now why is that? Why is that happening? Let me explain this to you. Look here, our atom was initially looking like this with 5 electrons and 5 protons. Now one electron has gone, which means now our Z effective is more. Z effective in this case is more, and Z effective in this case is less, because there were more electrons which were doing more shielding, which means that Z effective was less. Now more Z effective means that these protons are 5 and these electrons are 4. Now these electrons are getting maximum nuclear charge, force of attraction over them, which means it is now difficult to get rid of another electron because they are experiencing more force comparatively how much force they were experiencing before that, which means now Z effective in this case is more, and now the force of attraction is more, which means we will require more energy to remove an electron from B positive. So one electron which you were removing and you were giving some energy, that was lesser than how much energy you would be requiring to remove electron from B positive, because here in this case force of attraction is more. You getting it? So that is why we say that we will require more energy here to remove electron from B positive. This energy is more than the energy that is required to remove the first electron from boron, and this is how it is. Energy 2, ionization energy 2 is more than ionization energy 1. Now this I have explained to you that Z effective in this case is more and it is lesser in here, because you can compare the number of electrons and protons. Here as you can see, the number of protons you will be having will be 5 and number of electrons will be 5. But as you're gonna remove one electron and it will get converted into B positive, now you have 4 electrons for 5 protons, which means Z effective is going to be more in this case and less in this case, because more protons are there. They're exerting more force for just less number of electrons. Now what is for ionization energy? The energy that you were requiring in Z effective will be less. It will be less because there was less amount of force of attraction. Now the ionization energy in boron will be less, and ionization energy in B positive required will be more, because there was more force of attraction, which means more energy is required to get one electron out of this atom. Now let's understand the factors affecting ionization energy: half-filled and fully filled subshells. Now the thing is, these are stable electronic configuration. Let me give you an example. So now if you see anywhere these kind of the subshells, the subshells are half filled, and this type of configuration, if you get to see anywhere, these are half filled configurations which are stable, and fully filled configurations. Now for example, here is nitrogen and oxygen. Nitrogen has configuration, these are for the last shell. I have written the configuration: 2s4, 2p4, 2s2, 2p3. Now here p3 is half filled, which means it's more stable, and 2p4 is less stable, which means ionization energy that will be required in nitrogen will be more, because it's more stable. We'll need more energy in this case to get the electron out of the atom. Now after getting this electron out, we'll have this 2s2, 2p2 and 2s2, 2p3. Now here oxygen is more stable in this case, in case of O positive. In case of O positive, who is more stable? O positive, which means more energy will be required in this case. So ionization energy too will be more in case of oxygen, and ionization energy required in first case will be in nitrogen. Now the second factor is penetration effect, the closeness to electron. Now as you know, the s orbital is closer to the nucleus as compared to the p orbital due to penetration effect. Removal of electron from s orbital is therefore tough with respect to p orbital. Now let's take an example of beryllium with the electronic configuration 1s2, 2s2, and boron with electronic configuration 1s2, 2s2, 2p1. Now here in this case, as you can see here, the first reason is going to be, now here you can take the electron out from either p orbital or from the s orbital. As you know that s orbital is closer to the nucleus, which means the force of attraction will be more, which means z effective will be more, and therefore it's difficult to get the electron out of an electron which is closer to the nucleus, and therefore you're gonna get the electron out easily in case of this, where the electron is in p orbital, because p orbital is far from the nucleus. Now you get to know one thing, that ionization energy of one electron in that case, okay, for the first electron, in that case your ionization energy required in beryllium will be more from boron. Now after you get one electron out, now your atom looks like this. They have formed cations. Now let's compare them. Okay, now we're talking about the ionization energy 2 here in this case. Now as you know, this is an electronic configuration of a noble gas, which means now ionization energy required will be more in this case. Let's just mark it. Now the third criteria is Z effective. Now as you go from left to right, your Z effective increases as you go from left to right. And you should be knowing that as you go from left to right, your Z effective is increasing, which means your ionization energy is increasing. You will require more energy where the Z effective is more. Where the force of attraction is more, you will require more energy to get the electron out of the atom. Let's compare both of them. Lithium, beryllium. Now here the Z effective in this case is more, and in this case it's less. And so is the ionization energy. You require more energy to get the electron out from beryllium. Also, we can look at our previous example. Beryllium requires more energy than boron. But wait, boron comes after beryllium. Then why is it? It was an exception, because here the orbital was different. Here we have to consider the penetration effect. Okay, so yeah, you have to consider all the possible factors that determine the ionization energy, and then you can decide the final answer. Not just because beryllium is after lithium. No, that all like this. Now here, as you can see, that both of their configuration is 2s2. No, it's here it's 1 and here it's 2. Now you know that this is a noble gas configuration and it will be difficult to get the electron out from beryllium. And also you can consider these Z effective criteria. Now let's talk about the fourth factor, that is size. Now as you go from top to bottom in a periodic table, your size of an atom increases, and with that your ionization energy decreases. Now as you know that if you're going from top to bottom, your Z effective stays constant, whereas if you go from left to right, your Z effective, it increases. Yes, it increases if you go from left to right, and if you go from top to bottom, it is constant. So now, which means that if your Z effective is constant, you cannot decide if your ionization energy is going to be less or more with Z effective. But we can decide with the size. Okay, now let me explain this how. Because let's say this is a nucleus and it has just 2 orbitals. Because the size increasing from top to bottom, now an element which is at the bottom has more shells and an electron lying at the outermost shell. Now which is easier? Is it easy to get the electron out from the bigger shell that is really far from the nucleus, or is it easier to get an electron out from an atom whose shell is just close to the nucleus? Of course this one, it's easier, which means that the smaller the size, the less the size, the more the ionization energy, and then more the size. As you can see, the size is increasing here. As you go from top to bottom, the size is increasing. Now here, more the size means the easier it gets, the less amount of ionization energy it requires. So francium has needs less amount of ionization energy, whereas in case of lithium it's the maximum. And what about this metallic character I have written? Because as you go from bottom, as you go from top to bottom, you can see the size is increasing, and you require just minimum amount of ionization energy to get the electron out, which means that it can lose the electron easily. Which means this is a metal. What is a metal? What defines a metal? It means if an element has a tendency of to lose an electron from positive ions or cations, okay, that is what makes an element metal, if it is able to lose an electron. Yes, so if it is able to lose electron easily, it means it has more metallic character. Now this was all about ionization energy. So see you in our next video. Bye bye.